In the Beer's Law lab, we're going to measure the absorbance of several solutions that we know the concentration of, and we're going to use that data to determine the concentration of an unknown solution. So, let's talk about how a spectrometer, or in this case a colorimeter, works, because they work fairly similarly. So if we have our spectrometer or our colorimeter, we have to have some sort of light source. So we're going to pretend that's a light bulb. And our source of light goes through a filter, which filters out the wavelength that we want. And then that passes through our sample, which is our cuvette. And then it goes to a detector. So your detector can be a computer, or in this case, it can also be a lamp glass, which is what we're going to use. So what the detector actually measures is how much light was transmitted through the sample. And I couldn't make you do the calculation to go from transmittance to absorbance, but the LabQuest fortunately already does that for us, so we can just let it do the calculations for us and then record our absorbances. So you're going to take a stock solution of 0.50 molar copper sulfate, and you're going to dilute it using the values given in your lab handout. So for example, in trial 1, you're not going to put any stock solution, and you're going to have 6 milliliters of water. In trial 2, you're going to put 2 milliliters of copper sulfate and 4 milliliters of distilled water. So 2 milliliters plus 4 milliliters gives us a total volume of 6 milliliters. Now we are assuming the volumes are additive, which they are technically not, but for our purposes it's close enough that it's not going to affect our calculations. So to get the concentration of our diluted solution, we need to take our good old friend M1V1 equals M2V2, and we're going to plug in, we're starting with a 0.50 molar solution, and we're going to put 2 milliliters of copper sulfate in there, and we're going to dilute that to a volume of 6 milliliters. So we have M2 equals 0.50 molar times 2 milliliters divided by 6 milliliters. So I'm going to let you do that calculation and determine what the concentration of your solution for trial 2 is. Now you're going to do the same type of calculation for trials 3 and 4, and you're going to determine your concentrations for those. So then what you're going to do is you are going to go through and set up your LabQuest, and you are going to record your absorbances for each of your solutions. So when you set up your LabQuest, you want to be sure that you only press calibrate when you're doing the blank. If you press calibrate every single time, what you're doing is you're telling it that that solution is the baseline. So you're going to keep getting an absorbance of 0. So you only press calibrate when you are doing the blank. Then when you do your different solutions, when you start the data collection, only tap keep. Do not hit stop. If you hit stop, then what's going to happen is it's not going to give you a graph. You don't hit stop until you've done all of your solutions. Until you have done trials 1 through 5. Once you've done trials 1 through 5, then you can press stop. And you're going to record your absorbances for those, and then you're going to get your solution that has your unknown in it, and you're going to determine the absorbance of your unknown. So then what we're going to do is we're going to use the data that we have to determine our concentration of our unknown. So Beer's law, and no, we're not talking about beer that you drink. This is the Beer-Lambert law. We just refer to it as Beer's law. Beer's law tells us that absorbance is equal to the molar absorptivity and molar absorptivity is a constant for a given solution, but it is different for different solutions. So molar absorptivity is in units of moles, liters over moles times centimeters. B is the path length, and specifically the path length of your cuvette. Luckily in our case, and in most cases, the path length is 1 centimeter. And then C is our concentration in units of molarity, or moles per liter. So what you're going to do is you're going to take the absorbance is equal to, and we're going to fit this to the equation of a line. And you're going to get this data from your LabQuest. So if you think back to algebra, the equation of line is a y equals mx plus b, where m is your slope and b is your y-intercept. So if we compare this, on our y-axis we're going to have absorbance, on our x-axis we're going to have concentration, and then our slope is going to be our path length times the molar absorptivity. And then b is your y-intercept. Now you'll notice that nothing lines up with b, so theoretically your y-intercept should equal 0. In reality, it's not going to be perfectly 0 because there's going to be some background noise from the instrument and things like that. So you're actually going to end up with a very small y-intercept, but it should be pretty close to 0. And then what you're going to do with that information, your LabQuest is going to give you the data for what M and B are, and then you're going to determine the concentration of your unknown, and X is the concentration, and you're going to do that by measuring the absorbance. So you will get, let me get another color here, get one a little bit darker just so we can read it. The absorbance is going to come from your LabQuest, which you're going to measure. And your LabQuest will also give you the values for the slope and the y-intercept. So what you're going to do is you're going to calculate the concentration. And we can rearrange this equation algebraically. X is equal to y minus b over m. So if you wrote down your B and M values and you record your absorbance, then you can plug those values into the rearranged equation. And that's going to give you your concentration of your unknown. Now keep in mind that we only measure standard solutions from 0 molar to 0.5 molar. And we can't really extrapolate that line very far past the 0.50 molar. We don't have enough data to extrapolate that accurately. So, your solution, your unknown solution should have a concentration somewhere between these values. If you get something that's too much over the 0.5 molar, then you probably need to go back and double check your data and double check your calculations. So keep that in mind as you're doing the slab. So, Make sure you've read through your lab handout and you have submitted your purpose and procedure on Canvas, and I will see you in lab.